So now we'll move to electromagnetic induction. Like I said, it is the opposite of what we did in our previous lesson. In our previous lesson, when coin pass through a conductor and the conductor is in a magnetic field, it will experience a mechanical force. It will start moving. There will be a motion that will be generated when coin pass through a conductor in a magnetic field. Now, this time around, we want to do the opposite. We want to generate current by creating a motion in a magnetic field. That is what we call electromagnetic induction. So, what is EMI? Electromagnetic induction is a process of producing an induced current or an induced EMF whenever there is a relative motion between a conductor and a magnetic field. We can put it that way. Or whenever there is a change in the magnetic flux due to what? Relative motion between a conductor in and what? And a magnetic field. You can write that down, please. The definition of electromagnetic field. For example, here we have a magnet with a strong magnetic field. Now consider this cylindrical body. Let's suppose is a cardboard. Then let's wind around it a coil. So here we have this coil, is a conductor. So now let's attach to it a galvanometer, majorly to detect if there will be any induced current. So we notice that we can do three things here. This magnet can be fixed. We can move this set up, close to the magnet or away from it. Or make sure to stay. We can move the magnet towards it or away from it. Or we can move them towards each other or away from each other. So we notice that every time this conductor moves closer or away, this galvanometer will deflect. There will be a deflection there, meaning for there to be a deflection here, initially before moving it close to the field at all, the galvanometer shows no deflection. If we move it close to it, it deflects towards what? Positive side. When we move it backward, it deflects towards backward. So showing that current is there, because what galvanometer does is to measure little amount of current or PD. So in this case, something is obvious. When this conductor moves close, it goes through this magnetic flux, and hence induced current is produced. This is all called electromagnetic induction. Now we have three laws which are used in electromagnetic induction. I will start with the first one, Fleming's right hand rule. Recall we've done Fleming's left hand rule. Now let's go to Fleming's right hand rule. But before that, let's look into Faraday's law of electromagnetic induction. Now I've already defined EMI. Electromagnetic induction is a process where induced EMF or current is produced whenever there is a rate change in what? Whenever there is a relative motion between a conductor and a magnetic field, or whenever there is a change in what? Magnetic flux, which is caused by the relative movement. So Faraday law now states that the EMF produced during electromagnetic induction is proportional to the rate of change of the magnetic flux. The EMF is, directly proportional to the rate of change of magnetic flux. This is symbol for magnetic flux. We all know, we've done that before under magnetic field, that magnetic flux density is magnetic flux divided by area. So we can say magnetic flux is the product of what? Magnetic flux density multiplied by area, BA. So instead that the rate of change of the flux, meaning the rate of change of what? The magnetic line of forces, the more the EMF. But the thing is, we have a negative sign here. So negative sign indicates that before we can generate this EMF, work must be done. Work must be done on the system before EMF can be generated. So that's what this negative sign, stands for, which is explained by another law called Lenz's law. So Lenz's law is an energy conservative law. We are coming there. So, but we have this. Then from here we can say E equals to a constant comes in K. So this K actually is number of turn of the conductor. So we can use a loop. If it's one loop, N is 1, two loops, N is 2. So we can say our E equals to minus N rate of this. Now note that from here, the magnetic flux equals to flux density times area. We only use this if the conductor is perpendicular to the field. We know that from here, the direction of the field is from north to south. This is the direction of the field. So if the conductor is perpendicular to it, theta is what? So it's parallel to it rather, then our theta is 0, because 0 is 1. But let's suppose the conductor is inclined at an angle theta to it. So when we resolve to the horizontal, we'll be having what? BA cos theta. Then you will recall from simple harmonic equation that theta equals to omega t. So from here we can say our E equals to minus n. We replace this as what? D dt. Then our magnetic flux becomes what? BA cos theta, and theta is what? Omega t. So our E becomes minus n. Okay? First, magnetic flux and area are constant, so we can bring it out, and that will be what? BA, then d dt of cos omega t. If we differentiate cos, we get what? Negative sign. Hence, this becomes E equals to minus nBA times minus sine omega t. But omega t is another function. It's a function. If we differentiate omega t, we get omega times omega. From here, minus become plus. So I can rearrange this as B, A. I can write the omega, and this product of N, B, A, and omega. Then we have sine omega t. In short, we can say our E equals to BA omega N sine omega t theta sine theta. So this is the induced what? EMF. In terms of the magnetic flux density, the area, the angular speed, and what? The number of turns, then sine theta. So in this case, it means if you have to sketch this, if I draw this is a sine graph or is a sine function. So if you sketch the graph of E against t, against time t, because this omega theta is omega t, so we are going to have what? Sinusoidal graph. So meaning it's going to have a frequency. This is the first cycle, second cycle, and it goes. So meaning in this case, the EMF we are going to produce is going to be, sinusoidal. So it's like an AC, alternating current. And we can see from this graph, this is the maximum value of E. So we can call it what? E naught. The peak value of the maximum EMF that can be generated. And that occurs at this region. When the angle here is what? From here to here. One cycle is what? Is pi. Half cycle is pi over 2. And pi is what? 180. So from here to here is what? So it is maximum here. So whenever it's maximum, our pi has to be what? 90. So the EMF will be maximum when theta is 90. So when theta is 90 degree, meaning when the conductor is perpendicular to the field, our E becomes what? Maximum. So our maximum E max equals to BA omega N sine 90. Sine 90 is 1, so if we replace sine 90 with 1, the maximum EMF will just be what? BA omega N, which can be pronounced as bound. So this implies that what we have here, this bound itself is the maximum EMF. So we can say the EMF generated equals to the maximum EMF, then sine theta. So we are given an equation relating the maximum EMF and the EMF and the instantaneous EMF. We can get what? Sine theta. The most important thing is to know this formula and this relation. And also, they can ask you, for the EMF to be maximum, first, B must be very strong, meaning this B is what we call the magnetic flux density rather. So the strength of the magnet must be very what? High. Then the area, the wider the area, the more the what? EMF that will produce. Also, the more the angular frequency or the speed. So the faster we move, if this move very fast, back and forth, we generate what? EMF. If we move very slow, the EMF will be small. So a number of turns, and the angle also. It's maximum when it's perpendicular to the field. So we have to know that. We can also express this EMF generated in form of what? The length of this conductor L. The length of the conductor L and velocity V. So instead of using area and angular velocity, we can use length and what? And velocity, linear velocity. Let's do that. Let's just use dimension. From here, we can say we have B. Area is the product of two lengths. Then angular frequency is expressed as what? Number of cycles per time. So that's like 2 pi f. So it's like a number. If n is 1 and x is what? A number per time, can write as 1 over t. You know, omega is 2 pi f. So 2 pi is just a number. So it's like inverse of time. So if I take this one together, length over time, that's meter per second, it represents v. So this becomes what? BLV. So in terms of the length of the conductor, we can say the E generated, the EM generated can be expressed as B, length of the conductor, the speed of the conductor, sine theta. So these two are the same. This in terms of the area and the angular frequency or angular velocity. This in terms of what? The length and the what? Velocity. So the two works. So from here we can say the more the velocity, the more the EMF generated, and also the longer the length of the conductor, the more the EMF generated. Now let's talk about Lenz's law. So this law, Lenz's law, is an energy conservative law, because come think of it, if you look at it normally, it as though we generated what? A form of electrical energy from non-energy source, which is against the law of conservation of energy, which states that energy can neither be created nor destroyed. But Lenz's law states that, you know, when this metal approaches this magnetic field, so it is as though this end is like a north pole, and when north and north comes, they try to repel. So this magnet pushes this what? Metal backward, because this conductor itself, when current passes through it, will generate or will have a magnetic field around it. So it's as though when you have north, they are repelling each other, but you have to force your way in, you know. So in that case, the work you have to do, the extra work you have to do, multiply that, the extra force you have to apply. So overcome that repulsion, multiply by the distance you move, will give you the work done. So that work you did in the system is what generated the what? The current, the electrical energy. So meaning is as though you are converting your own mechanical energy to what? To electrical energy. So the energy is not created from a non-energy source. We are actually converting it from one form to the other. Like I said, we can explain using Fleming's right-hand rule, but let's move on. How can we state the law in case you ask? First, they can ask which of these laws is an energy conservative law. They'll put Faraday's law, they'll put Lenz's law, they'll put Fleming's right-hand rule or Klein's first rule. The answer is Lenz's law. So it states that the induced EMF, Lenz's law states that, can write, the induced EMF is in a such direction to oppose the motion that causes it, or to oppose the effect that causes it. And this law actually explains what happened to this negative sign here. So now let's move to Fleming's right hand. Look at this. This is my left hand, this is my right hand. According to these two are useless, you don't use them. According to Fleming's right hand rule or left hand rule, we have to place everything like this, perpendicular mutually. Same goes for this. So according to left hand rule, this represents magnetic field, this represents the current, and this represents motion. This left hand rule. For right hand rule, same thing goes. For right hand rule, this still motion, this current, and this magnetic field. And when you compare left hand and right hand, if you see, if the current flows in the same direction, or let's put it this way, let me try to draw it. Okay, don't worry. For left hand rule, we are looking for direction of motion. If this field and this current, the motion is conductor moving out. But right hand rule, if this still field and this motion, in this time around we want to get the direction of current. Can you see the direction of current? If you use the right hand, this is what you get. For left hand, motion coming towards you, current or field going this way, then the current is in opposite direction. So we use right hand rule to know the direction of induced current. if direction of motion and field is what fixed. So the current can either flow up or flow down, depending on the direction of field and what motion. So Fleming's right hand rule states that if the thumb, the forefinger, and the middle finger are held mutually perpendicular to each other, with the forefinger pointing towards the direction of field, and the thumb pointing towards the direction of motion, then the middle finger points towards the direction of induced EMF. That is Fleming's right hand rule. So left hand, right hand, we put them together. One thing differs, direction of current differs, which we can also explain using Lenz's law. And we can apply this when you are dealing with electromagnetic induction devices. We have some devices, they work based on the principle of electromagnetic induction. Example, a dynamo or a generator. So what a generator does is it converts mechanical energy to electrical energy. Unlike a motor, it converts electrical energy to mechanical energy. Then this time around, we want to convert mechanical energy to electrical energy. By the virtue of motion, we want to generate electrical energy. Now let's talk about generator or dynamo. We'll now compare with motor. But before that, I promise that I will explain something, eddy current. What is eddy current? So eddy current is normally due to electromagnetic induction. Suppose we have a metal sheet, let's say this copper or aluminum, a circular metal sheet. If this metal sheet moves in a magnetic field, what happens is, due to that movement, current will be generated. Or we can say EMF will produce. There will be an induced EMF. That induced EMF, according to Lenz's law, opposes the change that causes it. So in turn, that induced EMF will cause a current to flow through this metal sheet. And when current flows through a metal or any conductor, due to the resistance, it will be generated. So in that case, energy is going to be lost. And there's no how we can avoid this directly. Because as far as this is moving in that field, current is going to be generated due to the eddy effects of current. So due to electromagnetic induction, which will oppose the change that's producing it, and in turn it will waste the real EMF of the system. So in that case, how can we reduce eddy current? Or in short, let's define it in case you're asked what is eddy current. So we can say eddy current are circulating electric current induced in the conductor. Are circulating electric current induced in a conductor when it is placed in a changing magnetic field. It means the current flows in loop. It flows in loop in the earth. Although this eddy current has some advantages. For example, it is used to to oppose motion used in magnetic braking. So we call something magnetic braking. But in many regards, it has a disadvantage. So it has many disadvantages. So the question is, how can we reduce eddy current? Number one, we need to laminate. If we laminate the conductor, then eddy current effect will reduce. And also, we can make holes here. We cut off some parts here, several holes here. So if you're having hole here, the eddy current effect will reduce because the current cannot flow towards an open space. So by lamination or by creating a slot in between this hole, we reduce the effect of eddy current. But we still need the metal sheet there, and it will still move. So there's no how it will still be there, although the effect will be very small. So I believe you understand the effect of eddy current. And I think we made reference to this when we were explaining moving coil galvanometer. So they are desirable in a moving coil galvanometer. It has some application there too. So I think now we can now move to dynamo or generator and other electromagnetic induction devices. Here we have some electromagnetic induction instruments ranging from the generator, moving iron ammeter, hot wire ammeter, transformer, induction coil. Then we are going to talk about what we call HTT, high tension transmission. So we are starting with generator. So I think the one that will take our time more will be generators and transformers. And this will be the end of electromagnetic field. So what are generators? Generators are electromagnetic induction instruments that convert mechanical energy towards electrical energy, and they are also called dynamo. So So generators can either produce AC or DC. We've done AC circuit and DC circuit. We can have AC generator or we can have DC generator. An AC generator is also called an alternator, while DC generator in most cases is called a dynamo. Now, what is the key difference between them? Now, let's draw the diagram for the two. Similar to a motor, we have a strong magnetic field. Then we have the armature in between. Then we need, commutator. Then we have the split rings. On each side of the split ring, we have the carbon brushing. Then we have source of PD. If you look at this very well, it is very familiar. Yes, we've done this. What I do here is actually a motor, an electric motor. Well, when current is generated here, it flows inward. Direction of current, this is field. So using Fleming's left hand rule, current flows inward, field flows, this current inward, field north to south, and what happens? This thumb is facing down. So this part will move down, this part will go up. So this thing will rotate. We are converting electrical energy towards mechanical energy. This is a motor. Now, how can we turn this to a generator? This time around, we don't have electrical source. We actually want to generate electricity. So we want something to, we need a load to carry that out electricity. So then next, we will be the one to move this armature. We look for a source of PD, something that can rotate this. A source that will push this one down and this one up. So meaning we are having what? A source that moves this thing clockwise. When this is made to rotate clockwise from any source, if the source is from dam, let's say from water, so water can move a particular mechanical wheel. If that wheel rotates in the magnetic field, we generate what? Current. If you are to apply Fleming's left hand rule initially, if the current enters inside and the field, current enters inside and the field is from north to south this way, this thing is meant to come down. So meaning this current should enter. As you can see, in this case the current must enter this way. But if we rotate this thing, if we add a cell here, this is how the current will enter. It will enter here, then for this side it will go backward. But if we do electromagnetic induction, if we move this thing same clockwise, the current will not flow this way, the current will flow in the opposite direction. That's Lenz's law. So this is actually what we call it a DC generator, or we call it a dynamo. A dynamo and electric motor, they are identical. The only difference is that for a generator, which is a dynamo, a DC generator, it doesn't have electrical source, but it has a load. There are maybe a galvanometer here or ammeter that can read the value of the current produced. Or we use galvanometer since it's going to be small. So, but most times what we need is actually an AC. We need AC generator, alternator. So, meaning we have to convert this DC generator to AC generator. I believe you already know the difference between DC generator and electric motor. They have the same diagram. The only difference is that for DC, for a DC generator, it doesn't have what? Battery, sort of EMF. For a motor, it has a battery. And unlike a motor where we generate mechanical force, here we use mechanical force to generate current. So we can convert. Note this this question is very they do ask this question very well. This generator can be converted to AC generator, and AC can also be converted to DC. But since we have DC on the board, how can we convert this to AC? DC can be converted to AC generator by replacing the split ring with two slip rings. We replace this split ring. The split ring is replaced by two slip rings. How? Let's draw the diagram and let's compare. They are still the same thing. So let's replace this split ring here with two slip rings. Then let's put a carbon brush. So now, when we replace the split ring with slip rings, we turn this DC generator to AC generator. Same way, if we make it rotate clockwise, So clockwise means this side is going up. So this one is going down, this one is going up. This one is going down, this one is going up. So in that case, let's look for direction of what? Current, in this current. Is the current going to flow this way or this way? So let me right hand rule now, right hand rule. So field, north to south. They will focus on this side. This side, the current is down. Current is down, field is this way. The turn point inward. So mean the current has to enter inward. This is the direction of current. Direction of current, it will go inward. Flemish, right, and rule. So this is what? This is generator, this AC generator. We can always turn AC to DC or DC to AC. From AC to DC, we replace these two slip rings with a split ring. From DC to AC, we replace the split ring with two slip rings. And now we can convert this DC generator to a motor by putting a source of what? EMF there, and the current will start flowing. And this thing will start what? Rotating. It will have a tug. I think with this we are done with generators. Now let's move to moving iron ammeter. Please just take note of this. Listen, take note. So you can write, listen and write. So unlike moving coil galvanometer that we've done, moving iron ammeter measures both DC and AC. Note, moving coil galvanometer can only measure DC, while moving iron ammeter can measure both DC and AC. And it is cheaper and easy to make, but it operates based on the principle of what? Electromagnetic attraction, or repulsion, where iron moves in response to the magnetic field whenever there is what? Current flowing through it. So that's electromagnetic induction. So the main difference is between moving iron ammeter and moving coil galvanometer is that moving coil galvanometer can measure only DC. This can measure both AC and DC. It is cheaper to make, although moving coil galvanometer is still better. It has more accuracy. That's the major point you have to know. So the next one is hot wire ammeter. So for hot wire ammeter, this operates based on the heating effect of current. Now, since heating effect of current does not depend on the direction of the current, hot ammeter can also measure DC and AC. So majorly hot wire ammeter measures both AC and DC also, but this one works based on the principle of heating effect of current. The heat generated when current passes through a conductor is I square RT, depending on the resistance and the current flowing through it. So the next is to talk about transformer. But before that, let me quickly talk about HTT, high tension transmission. What is HTT and why is it important for us to discuss? When electrical power is generated from a source, like in dam, what will actually happen is we want to generate electricity. We actually use electromagnetic induction, that's generator. But in this case, we will need a constant source that will keep moving the coil, which the water gives us. The dam, they move with very high speed because they are confined in a region and only a little space is made for them to come out through. So that speed is made to rotate some mechanical gear, so that cuts or change magnetic flux, they will generate what? So if the power is generated, we have to transmit it to the drain where it's going to be used, and that distance is very long. For example, in Nigeria, we have what we call the Kanji Dam in Niger State. We call it the power state because large amount of power is generated in the state. So if we have to transmit that to other parts of the state or even outside the state, the thing is the metal we are going to use, or the conductor we are going to use, the wire, since it's extremely long, the resistance of the wire is proportional to the length. If the length is long, the resistance is very high. Now, since R is very high and the current will pass through with in a large amount of time, it can spend days or even months where the current will keep flowing. So R is high, T is high. The heat generated will also be high. Now, if the current is also high, we now square it again. Then it means the heat generated will be too much. And in that case, the wire will melt, and after that, it's cut off. And the whole process has been what destroyed. So what can we do? We cannot, for R, the only thing we can try to reduce R. The length, there's nothing we can do with the length, but we can try as much as possible to ensure the wire is thick, because resistance and area, they are inversely proportional. So I have a thick wire, resistance will be lower. So we use a thick wire, that's it. For the time, there's nothing we can do except we want to be switching it on sometimes or switching it off. So, but for the current, we can control it. We can transmit power at a very low current. But note, power is IV. From here, we can say V equals to P over I. If the current is extremely low, because from here, at constant power transmission, voltage and current, they are inversely proportional. So if the current is extremely low, because if current is extremely low and we square it, if we square a small number, it gets even smaller. If I have 0.2 and I square it, we'll get 0.04. It gets smaller. So if our current is very small, the heat generated will be small, and in that case, the heating effect will reduce. Then we can still go on with the transmission. But the thing is, if the current is really small, the voltage is very high. So that's what we call the high tension. So high tension actually means what? High voltage transmission. The voltage is high, the current is low, and the voltage can reach about 50,000 volts from the source. And this is too much. So when this thing gets to the community, the voltage is too high, then we have to reduce it to a value. In the power line, we can reduce it from 50,000 to around 5,000 volts. Then this factor is still too much. So we see how to reduce this one to about 240 volts, which is what is supplied, to most houses, 240 volts. So the device that will help us to step down this voltage from 50,000 to 5,000 to 2,400, is the transformer. So transformer is important, which will be next we're going to talk about. Transformer. So after discussing transformer, we'll now talk about induction coil, which is like a special case of transformer. In that case, it's like opposite of this. It's like a step-up transformer with some differences. So in short, we'll discuss about generator, moving iron ammeter, ultra ammeter. HTT, high tension transmission, is a process whereby electrical power is transmitted at low current and high voltage in order to reduce the heating effect. Then to step down this voltage back to the usable value, we need transformer. So we explain transformer, and if you explain transformer, we'll talk about induction coil. Remember, the first time I mentioned induction coil during this process is during capacitance. So I explained that capacitors are used to eliminate sparks. They are used to eliminate sparks in induction coil. So because in induction coil, a lot of sparks are produced during the process whereby voltage is step up. So we use capacitors in that regard. So we are going to talk about transformer, then induction coil, and that will be the final end of electromagnetic induction, or everything on fields. Transformers. So what are transformers? Transformers, or let's say transformer, works on a principle of mutual inductance, which is a specific application of electromagnetic induction. So what is mutual inductance? Like I said, it is a specific case of of electromagnetic induction. But basically, we can just say a transformer is an electrical device used to increase or decrease alternating voltage without changing the frequency. So the question is, what is mutual inductance? This is a type of electromagnetic induction where a changing current in one coil produces a changing magnetic field, which induces EMF in another nearby coil. And this is exactly how transformers work. Suppose I have a coil here, and we have AC current flowing through this coil. When the current flows through the coil, what happens? Magnetic field will be generated. If we now have another coil that is close to it, what happens? Due to the fact that there is going to be magnetic field around here, so this particular coil here will induce the second coil to also be magnetized, and in that case, it's also going to generate current. So what happens is as though we are transferring electrical energy from, we call it the primary coil, to the secondary coil without motion. No physical motion is occurring here, but what happens, we've transferred, and that makes transformer the device with the highest efficiency in the world because it has no moving parts. because whenever there is movement, there must be work done against friction, and work done against friction takes the largest percentage in the loss in every machine. Although there is no moving parts, so our assumption should be that the power generated in the primary coil, let me call it PP, and the power generated in the secondary coil ordinarily are meant to be the same, meaning there shouldn't be any loss. But the thing is, there is still going to be losses. Yes. In fact, we have 4 losses. Although all those 4 losses, we can reduce them to bare minimum. And after reduction of that, after we try to reduce them, the transformer, the efficiency of a transformer can be as much as, let's say, 99%. But if we have this case, this is an ideal case. This will only occur if we have ideal transformer, but ideal transformer is only what? Practical. For ideal transformer, power in the primary coil equals to the power in secondary coil, no power is lost. We know power is IV, so we can say IV equals to IV. This is primary, this is secondary. From here we can say V secondary over V primary equals to I primary over I secondary. If we cross multiply, we still get ISVS here, VPIP. So the ratio of the PD in the secondary coil to the primary coil, we notice that if we are to count the number of turns in the primary coil, here we have 1, 2, 3, 4, 5, 6, and here we have 1, 2, 3. So 6 over 3 is 2. We'll call that the turn ratio. And if you divide the voltage here to the voltage here, well, we are also going to get a 2. That's what we call the turn ratio. The turn ratio is the ratio of the number of coils in the secondary coil to the primary coil. So turn ratio N. So we can put this at the back of our mind, but note this only works for an ideal transformer, a transformer that is 100% what? Efficient. If you assume it is 100% efficient, meaning it has no loss. So the current, but note this current are AC. If the currents are not AC, then the transformer is not going to work. So they are AC what? Current. So this is the IP. So the voltage across here is VP. So what we use here is what? IS. The voltage here is what? Is VS. This is for an ideal case. Before we talk about the losses, let's talk briefly on practical transformer. Although we are not going to go in depth, you do that in advanced level. So let's talk about it very brief. Practical transformer. For a practical transformer, there will be losses. So meaning the power in the primary coil will be greater than the power in the secondary coil. Meaning there will be a loss. And the loss in power equals to what? Power in the primary minus power in the secondary. So in this case, we cannot talk about the efficiency of the transformer. In this case, it's going to be the power output over the power input times 100%. So this is the efficiency of the transformer. And the connection between power output and power input, meaning power in the secondary coil over power in the primary coil, this is the connection between them, in case you are given the losses. So with these two, we can solve any question related to efficiency of a transformer or loss in transformer. Then lastly, what are the losses in transformer? Losses in transformers. We actually have 4 losses, which I will abbreviate as its L, because in L we have what? A lot of heat generated there. So we have its, we have H, we have E, we have L. So what is it? It is just heat loss. Because current will flow in the coil, and the coil has resistance, so there is no how heat will be generated. So we have what? Loss due to heat produced in the conductors or in the coil when the current passes through them. Then this H is called the hysteresis loss. This is the eddy current loss, which I mentioned before, I've explained before. And this is what? Loss due to the leakage in what? Magnetic flux. So we have Joseph's loss, hysteresis loss, eddy current loss, and loss due to leakage of magnetic flux. How can we now reduce it? Let's take them one by one. So Joseph's loss is the energy loss due to the resistance of the coil. The coil will have resistance. Due to the resistance of the coil, this can be reduced by using a thick wire of low resistance. So this is the heat loss. we use what? A coil that has low resistance, and it should be thick because the resistance is inversely proportional to area. So the wire should be thick and low resistance. So just heat loss can be reduced by using a thick wire of low resistance. Then the next is hysteresis loss, which is the only terminology I believe I have not made mention at all. So hysteresis loss, this is the energy wasted due to the reversing magnetization of the coil. So you know the coil will magnetize, will demagnetize, will magnetize and will demagnetize. In that case, you know, there is a kind of loss called hysteresis loss. You know, inside this transformer we have what? Soft iron core. That soft iron core, when AC is flowing, you know, for AC current it has what? A frequency. So sometimes it goes on, sometimes it goes up, you know, it's sinusoidal. So in that case it means we are going to have average current. So similarly we are going to have what? Magnetization, demagnetization occurring simultaneously, you know, from time to time. In that case, that's what we call hysteresis loss. So in that case, to reduce hysteresis loss, we have to use a special alloy like the soft iron core that can easily magnetize and demagnetize. So since soft iron core can easily be magnetized and demagnetized, to reduce hysteresis loss we should use what? A soft, you know, iron core. We should not use steel, because for steel it cannot easily demagnetize or easily magnetize, although it can maintain its magnetism for a long time. So we have to use a soft iron core in the transformer. The next one is the eddy current, and I believe I've already explained eddy current. So eddy current, this is produced by the varying flux cutting the iron core, and the efficiency is reduced, meaning there's a loss because the power produced in the primary coil. So there's a kind of what? Power produced in primary coil due to what? This eddy current loss. So in order to reduce eddy current loss, we have to laminate the coil, which I said initially. We laminate. So meaning eddy current loss can be prevented or can be reduced by lamination. No. When we laminate the coil. And as for the leakage, so this arises because not all the lines of induction passes entirely through the iron core. Exactly. So some are outside. So this can be reduced by special forms of what? Coil winding. We have different style we can wind core around what? You know, special coil winding. So if you do special coil winding, it's going to reduce the lines of induction that will not pass through the iron core. So by doing special coil winding, we can reduce what? Leakage, or we can reduce loss due to the leakage of what? Magnetic flux. So transformer have very high efficiency if all these losses can be prevented or reduced. So this one we have what? Special coil winding. And these are typical jam questions. Can ask you, how can hysteresis loss be reduced? By using the soft iron core. How can we reduce eddy current? By laminating the what? The coil. Then next, how can we reduce loss due to leakage of what? Magnetic flux? By using what? By doing what we call a special coil winding to maximize the amount of induction line passing through the what? The core. Then to reduce heat loss, we use what? A thick wire of low resistance. It's thick soft lamination coil, or lamination special, or lamination winding. I just try to get form an acronym that you can easily remember. Let me write it now. It's L, or you can say L it. So just heat loss can be reduced by using a thick. This thick means thick wire of low resistance. Hysteresis loss can be reduced using a soft iron core. Eddy current loss can be reduced by what? Lamination, by laminating the what? The core. Then loss due to the leakage of the magnetic flux can be reduced by doing what? Special coil winding. So it's hell. So with this, I believe you can easily remember the losses in transformer and how they can be what? How they can be reduced. The last thing before we end the topic finally, induction coil. So right, an induction coil is an electromagnetic induction device which is used to convert a low PD source to a high PD source. Suppose we have a source of PD that is 2 volts and we want to amplify it to, let's say, 20 or let's say 200 volts. What we use, we call it an induction coil. So it's like they're like step-up transformer. Oh, I think I didn't mention that the other time. Transformers can either be step-up or step-down, but most transformers we have, they are step-down to reduce voltage, high voltage, let's say from 5,000 volts, all step it down to 240 volts. So they are step-down transformer. In short, for step-down transformer, the turn ratio is less than 1, meaning the primary coil has more ratio than secondary coil. So example of a step-down transformer, something like this. So like the one I do is a step-down transformer. But in a transformer, what flows is an AC. Because AC change direction, what happens, this or that change in direction, there's an induced what? So there's a magnetic field that will be formed in this coil, which will induce current in the alternating coil. But unlike inductor, what is flowing is not AC, it's actually DC. But if this is flowing in the coil, they cannot be induced current in the second coil. So what we can do is to get something or like a key or a switch that can turn the DC off and on at a high frequency. So maybe every 2 seconds we switch on the DC, we put it on, switch on, switch off. So that make and break, that on and off, that DC will create a kind of alternating current. Although it's DC, but the DC will behave like AC in that case. So in this manner, we can actually produce high PD from low PD. So the secondary coil will have more turn. So the turn ratio here is greater than 1. So induction coil is like a step-up transformer. Although instead of having AC, we are having EC. We are having a DC that is being switched on and switched off, with time by what we call a vibrator. But during this process, a large amount of sparks is produced or are produced. So to eliminate the sparks, we use capacitor, or we use them as what we call condenser. So in summary, the main part of the induction coil, the primary coil have few turns and thick wire. Then we have the secondary coil, many turns with thin wire. This wire is very thick. This one is thin. Few turns here we have a large turn. Then we need a soft iron core to strengthen the magnetic field. You know that before. Then the make and break mechanism, the vibrator, that will switch on the DC and switch off. So the current seems like an alternating current, although it's DC. Then we need the capacitor as condenser to eliminate the spark. Apart from the fact that the capacitor is used to eliminate spark during the switch, the make and break system, it makes the current break faster and sharper because it stores energy, and it increases the induced voltage. So now we're having 3 uses of capacitor. 1, to eliminate sparks or to reduce sparks. Secondly, to make the break faster and sharper, the current breaks, the on and off. Then to increase the induced voltage. 3 uses of capacitors in induction. With this, we've come to the end of fields, from gravitational down to electric, down to magnetic and electromagnetic field. This is the end, and our advice. While watching the videos, try as much as possible to take notes. All the points I mentioned without writing, write them in your notes. When you just listen, you can easily forget. But when you put them down in your notes, you can recall, you can revise, so you don't have to watch the video again. But if you don't make notes, you might forget and you might still have to waste your time to watch the video again. So please always try to make a detailed note. And after making a detailed note, I will still advise you, go to your textbooks, make further findings, and you can even develop your own notes by yourself, so that you can easily understand your own language, form acronyms for yourself. Physics is extremely simple, but you need to do something extraordinary so that you can master it. If not, it becomes difficult. Thank you very much. We've come to the end of about 90% of physics with this class. We are done with mechanics, we are done with thermal, we are done with waves. Now we are done with fields. What is just left is atomic physics. We'll talk about atomic models, energy quanta, and wave particle duality of light. Then we'll talk about nuclear physics and basic electronics. See you in my next class. Don't forget to always like my videos, like, subscribe, watch, and share with others. Thank you very much.